Okay, welcome to an exciting Arduino class. Oh boy, I see you guys shiver with anticipation. If you came to class today, you got an Arduino. And if you didn't, well, one bad plus one bad equals two bad. And that's too bad on you, because you don't have your Arduino, and that's because you're not here. Now you could say I discriminated against you because you didn't show up. And that would be true. Too bad. Now you could say, but you should be more sympathetic to those individuals who don't show up, Professor Lyon. No, I shouldn't. It's all right. No, You wanna get your Arduino and take it home with you over the break. You gotta come to class, and that's it. So, anyways, after that little display of irateness, I thought what I'd do is introduce you to my good personal friend, Hello World. You're gonna enjoy this. The Hello World program, after you've installed your Arduino, let's go to the install section now before I get too far ahead of myself. You want to go to Google and say Arduino download. Okay? Click on download the Arduino software. Take note of the fact that there is a beta version. I wholeheartedly endorse the idea that you completely ignore the beta version, because I will. Click on Arduino 1.05 and click on the version of the Arduino code of your choice. I'm thinking it's probably Mac or Windows. And if you're a Unix person, forgive me, but there is a Unix version and I have tried it. And it does work. Has everybody downloaded the software now?
Yeah, we should click on Windows Installer.
Yeah, you can do the Windows Installer. If you haven't done the installer yet, I've got it down here on my little USB key. And you can certainly plug it in. You haven't done that yet? You've been sitting there. You got the zip file? Well, that might work. You just got to uncompress it then.
Yeah, it's still extracting this stuff.
Wow. You want the installer instead?
I just click on it.
Okay. So anyways, after you've got your installer happening, you could plug your Arduino in. And your first order of the day is to see if you can get the Blink program to work. So what I'll do here is I'll go to my examples and I'll go to Blink. And I'll just run right through the setup on this real quick. Go to your tools, go to your programmer, and select AVR ISP Mark II. Then go to the board and select Arduino Uno, because that's what I got here for you. If in your infinite wisdom you do not select these things, you will get an error. And I can demonstrate that error for you. So when things are hooked up properly, you may have a COM port selected, and it may be either COM1 or COM4, or if you're on a Mac, it could be 2215 USB or something like this. If things are working properly after you select examples Blink, you should be able to do an upload, and it should say over here uploading, and then it should say done uploading. Fast. If you did it wrong, and I'll give you an example of doing it wrong, I'll pick the Dua Milanove. So I picked the wrong model, deliberately. And then I'll try the upload, and I'll get a cryptic little error in here that says something like AVR stack blah blah blah. And you can see it's not uploading right away, and he's trying to communicate, and he's getting a communication error with the board, and he says, AVR dude, you can tell this is written in California, right? STK 500 get sync. What? Then it says not in sync, RESP 0x00. What that says is you set it up wrong. That's my translation. Now there are two reasons you could have had it set up wrong. Either you got the wrong board, that's the case for me, or you got the wrong serial port, which could also happen. So here, if I switch to COM4 and try and do the upload, because there's no Arduino at the other end of the COM port, it tries to do the upload and then it dies horribly in flames with the same AVR dude and the stack whatever. And I wish I could tell you what all that really means, but all I can say is, sorry, AVR dude, stack 500 get sync, not in sync, RESP 000. So to fix the problem, it's got to be one or two issues. It's either you got the wrong serial port or you got the wrong board. And once things are happening, you can do the upload and things will start to work. And now it says done uploading. And I should have a blinky yellow light, which I will hold up for you all to see. And now I'm going to change the blinky yellow lights on time and off time. I'll change it to 100 milliseconds from 1,000, and it'll be on for 100 milliseconds and off for 100 milliseconds. So I'll get a total cycle of 5 blinkies per second. And so now it should go, yeah, there's 5 blinkies per second. And now you can sort of see it's going on and off at 5 times per second. And that's it. How you doing over there, Mike? So now that things have been installed and you've got your Arduino set up and running, right, Mike? I feel bad. I mean, you've been sitting there doing this install for 20 minutes now. Is it done?
Yeah, it's coming up.
All right. So now what I want to do is introduce you to the idea that you can get a print statement that will print to the serial port, and you'll be able to see what is going on inside of the little micro brain that is the Arduino. So the first thing I want to do is I want to write a little program, and I started off with bare minimum, and I set up a little here, let me comment everything out just so that we can kind of get the bare minimum thing to run. So I'll comment everything out, and all I did was I said serial port begin 9600 baud, and there's a section in this code that says setup, and that gets one once and only once. And then there's another section in here, and it says serial.println, and then there's a string inside, and it says biomedical signal processing, which sounds very hoity and toity. And so what this should do is it should print out to the serial port at 9600 baud the message biomedical signal processing. There's also another main loop which gets executed repeatedly, and in that main loop I just threw in a delay of 1000 milliseconds. So after having done all of that, I should be able to get a compile and an upload, and it says uploading, done uploading. So now if I go over to my serial monitor, which is different than the serial port, if it's set to 9600 baud, it says biomedical signal processing, and that's all good. And that is what I wanted to demonstrate. So now I've got a mechanism by which I can communicate back to the host computer. Let's put in to this delay loop this basic idea that we're going to be printing something once every second. So we'll start off with a variable. Let's call it int I. We'll set it equal to 0. Then what we'll do is we'll put in a print statement, serial.println I semicolon, put in our delay, and then at the end we'll say I++. Now what do you think would happen if we did this and ran it? You think? I'm not so sure. It's going to reset to 0 each time, right? This is an error, right? Because now it says done uploading. We'll go back to our serial monitor, and it should say something like 0, 0, 0. So what has happened is we've got locally scoped variables that are automatic inside the loop statement here. That integer I equals 0 is an automatic variable, and it got set to 0 each time. So suppose we said something like this. Suppose we went outside of the setup and we made globally scoped the variable integer I equals 0. Now what do you think is going to happen when we run our little program? Now it's going to count. So what have I done in this illustration is I've demonstrated that there are two kinds of variables here in this program, some which are locally scoped and some which are globally scoped. 0, 1, 2, 3. It's counting. I'm the count and I love to count. 1, 2, 3, 4. Right? It's great. So once the computer can start to count, we can do things with the computer. Like we can set up an array. So here's a little array which I'm going to set up, and I'm going to do this in the initialization part. And through the magic of magic? Is it magic? Through the use of the syntax that you are used to in Java, I'm going to use that Java syntax to establish the initial values of the array. I'll use this global variable integer, set it equal to 6, which will give me 6 elements in the array. And then I will proceed to allocate the 6 elements using my little int declaration. And then I will set the 6 elements. And now in my loop statement, I'll use I to actually print the values of the 6 elements. R of I. Now what do you suppose is going to happen? What will happen at the end of the array? An array out of bounds exception at runtime is what a well-behaved Java virtual machine would report. What do you suppose will happen to the poor Arduino when we start to stomp all over its memory and try and print this array without having actually allocated anything beyond the end of the array? Well, if it was a Unix program, it would say segmentation fault, core dumped, and then you could proceed to debug the core. But because we're in a embedded microcontroller, it's anyone's guess. Let's see what happens. So he says that he's uploading and he's done uploading. Let's look at the serial monitor, and what do we get? 0, 1, 2, 3, 4. Wait for it. Ooh, that's interesting. It's reading into Arduino memory. Memory that it shouldn't be at. Memory that it has no business being in. In other words, we can proceed to go into program memory and start writing in values even though we shouldn't. Now, this is an interesting point about protected memory. The Java virtual machine doesn't pass in pointers. It passes in references, and it monitors your reference to Java virtual machine heap, and when you go out of the bounds for the end of the array, it throws an exception at runtime, an array out of bounds exception. But here in C, you can do what you want. It doesn't care. And what happens in Windows when you start to do what you want is you get the blue hex codes spilling out all over your nice clean floors, and you say hi to Dr. Watson. So in effect, C is not a, I'll call it, protected memory language. C is a language that lets you do what you want. It's a very powerful gun, and you can shoot yourself in the foot with it. And if you shoot yourself in the foot with a powerful gun, don't come crying to me. Hey, Kev. I got you an Arduino, and we're set up here, and we're doing a little Arduino download and programming. Do you have a laptop with you?
Yes.
Great. Does it have the I don't know if Windows 8 runs under the 1.05 to catch up a little bit. Basically, you need to install the exe file, and then you need to plug in the Arduino to the USB, and then the USB into the laptop, and then we'll see if we can't get you caught up real quick once you're installed. So at this point now, what I've been wondering is, what would it be like to try and see if we could establish something that runs like the DFT. Now, if you recall, the DFT was not a fast Fourier transform. I don't know if you guys remember this, but the DFT for Java was a I think we said yes, an order n squared algorithm. This is what it says right in here. But having said that, a short DFT can sometimes be faster than an FFT, especially when n is very short. So I had this idea that we would use our little main method in here to try and drive our slow, discrete Fourier transform, and that in the process of doing that, we would, let's say, attempt to benchmark our ability to do some elementary spectrum analysis on our tiny little 8-bit toaster controllers. Ooh, how exciting! DFTs on Arduinos. Isn't that exciting? Yes. Wow. Yeah, if it's not exciting, I feel sorry for you, because it doesn't get better than this. And that's it. So there. So let's go back to our simple DFT example. And this is the one where we're going to try and make a ramp. So for making a ramp, you think I could just cut and paste something like this? Probably not, right? This is not one of those things that's just going to work without change in my Arduino, right? But I'll try it. I mean, this is just bad practice all around. But if what you wanted to do is make a ramp, what you could do is you could sort of put in the Java code, paste it into the comment, and now look at it and say, gee, if what you wanted was a ramp that ramps up from 0 to n, that's kind of what we have here. That's our ramp. And so if what you want to do is establish this as your ramp, I really don't need a subroutine. Instead, what I can do, it's so hard to control this. I don't know why. I'll just call this ramp. That's my ramp. Call this ramp, R-A-M-P. And then if you recall, we used n as something like 8. That's an integral power of 2. Why does this say IntelliJ Code Insight folding transform? God, class not found. Oh, I was pasting in here and it gave me a hard time. How about that? Let's just see if this compiles. Oh, this has to be called ramp. What else? Ah, he's good. So what shall we do in order to be able to do our analysis? Seems to me like we're going to need a real part and an imaginary part, right? And if we look back at what we called the real and the imaginary parts, it was R data and I data. And they both had to be the same size as the ramp data. So what we'll do is we'll say something like this. integer r data of n, and then integer I data of n. And I'm wondering if I can use n in here as well. Now, will C allow me to do that? To define int as n as 8 and then put it into the sizes of these arrays? And the answer is no. What if I put the 8 in here as a constant, and the 8 goes in here as a constant, and the 8 goes in here as a constant? Will that be permitted? And the answer is yes. So what can we do you think, in order to parameterize something like the size of the array so that we can have a static allocation of memory at compile time? Any ideas? How about if we use the define statement? What if we define with a pound sign, and this is something which we don't get in Java, what if we define n to be 8? Ah, n now he's giving me a hard time about it, right? So what's the define, we'll call it the define syntax. Suppose you don't know C. I think that's a fairly safe assumption, right? You can always look up define for Arduino in code, if you like. And you should be able to learn how the define works. Or there's another way to go. But here it says constant name and then value. So this is what I got, constant name and value, and that seems to work. And I can even put, well, let's see, we got n in here. Well, I is less than n. Can we get another constant in here? Integer size of array, what do we call it? S equals n. Can I put s in here? Will that work? No, he's unhappy. So it seems to me like I gotta say integer length equals 8. And now I can say, well, I is less than length. And then it should work. No. What could be the problem here? What if I said, well, I is less than 8? Will that work? No. Something is wrong. Can anyone see it? I'll take this out. I think the define statement is incorrect. There must be something wrong with the way define is defined. Yeah, he's not happy with the define statement, so I'll leave it out for now. We'll put in the length. And I gotta say, my C is very rusty, but it seemed to me like the define statement was fine. Here it says pound sign define constant name value. Yeah, I'm not seeing why that should be an error, but maybe you can see it. So now I've got my little ramp, which goes from 0 to length and size. And then I can go through here and I could print out my original ramp, if you like. Ramp of I. And now I'm ready for doing the Fourier transform. So now let's do the implement the discrete Fourier transform. I'll just call it DFT. Here. Alright, so what now? You can't sit like lumps on bumps or I'll just assign it for homework. I've already got an allocation here. There's my DFT. I don't need to normalize the data yet. Okay. I've got some input data on the DFT. Shall we experiment with the idea of calling a subroutine? Would that make sense? Alright, so let's do that. Suppose we had this strong desire to create a subroutine. Void print high. And the subroutine print high prints a serial dot println quote hello world end quote end paren sem. And what we'll do in our little loop is we'll call print high. Okay, so that's fair. Now I've got my first subroutine in the Arduino, and it's going to print hello world. Let's see if this compiles. And he's unhappy. So what's the problem here? Oh, print line is wrong. Okay. And now what do we got? Great. Let's upload it. Go to the serial monitor. He says it's done uploading and it's printing hello world once per second. So how about this? Suppose we pass in a value. Suppose the value is integer q. And what we do is instead of printing hello world, we print q. And what we do is we pass in a number like 100. Or let's pass in, I got a good one. Let's pass in I. Right? A nice variable. So now let's try and do that. Let's see if we can get a clean compile. And he says he's uploading. Here's the serial number, serial output. Now he's passing in a value, passing in I by value, and it's printing it. So that's pretty clear, right? You can pass arguments into subroutines. Good deal, right? Suppose I want to pass in the ramp. Okay. Let's take the ramp and we'll create a argument for the ramp so that it's an integer array R. And what we'll do is we'll make up a little for loop for integer. Oh, I know. We'll print R of I. Good deal, right? Because we know I is changing, so that means we're going to have to get I in there as well. R of I. But I is global, right? So if I is global, we already have I. We should be able to access it. R of I, that's the ramp. So in principle, this will print numbers 0 through 8, and then it'll go off the end of the array. But that's okay, because in C you can do what you want. C doesn't give you protected memory, so if you want to go stomping around in the memory of the Arduino, that's cool, it'll let you do it. You want to crash the computer? Go right ahead. You're the only one using it. It has no operating system. You're on your own, buddy. So let's go back to the monitor and see what happens. And it's starting to print out 0 through 7, and then it's going to go off the end of the array, and then who knows what happens. Garbage. Gesundheit. Yeah, so there's garbage all over the place, and there's the junk in them, and it's all over. Sloppy code. But it works, so I don't care, as long as it works. So what do you think of that? I can pass arrays into the subroutine. That's good, right? Sure. Why not? How about this? How about if I take an array and pass it back? Can I do that? So what if you said to me, oh, I know, let's create a double precision number, double array of junk, and then when it comes back, I'll allocate it. How can I do that? Well, let's see. Double foo array. I don't know. It's got like, I don't know, some numbers in it. 6. And now I'll make a little for loop for integer k equals 0 while k is less than 6, k plus plus, and then foo of 6 is equal to k squared. So foo of, let's say, foo of k equals k times k. And then at the end of the day, we return foo. So it's just like Java. It's just like Java. And then when foo comes back from an invocation to print high, what do we have? Oh, I know. Double need a variable name. How about wow equals print high, and what we'll do is wait a second, and then we'll say serial serial dot print line, and then we'll say wow of I equals end quote end paren sem serial dot print line of wow of I. So this is going to return an array. I'm going to be able to go through this array, and I think I can print it one element at a time until I get off the end of the array, and then something bad will happen, I should think. But let's just okay, what's the problem here? Do we have to declare? Declare functions for the Arduino. Declare function return array. He doesn't want you to pass back a function. So here he wants you to pass in a pointer and then change the array by side effect. So unlike C++ or Java, it doesn't look like you can return an array after doing an allocation. Is that consistent with your understanding of how the Arduino is programmed? Returning arrays. This is really what I wanted. I thought you should be able to do that. It looks like he's pretty unhappy with that. So he wants to do it with pointers. So your only option here, unfortunately, is to pass in foo as an array, and then have it changed as a side effect. And so what that means to me is that foo is going to have to be a declaration outside in global variable land, and somewhere in here we're going to have to define foo. Now I guess that'll be in here, and we won't return it because it'll be changed as a side effect of the invocation. What a pain. And so then when we go through and print out foo, it'll be a global variable foo of I. Print high is going to need foo as an argument. And foo of I comes in here. Well, let's see if that works. Oh, this has to be ints. Maybe that's what he was troubling about. Alright, so with foo being an int, we pass foo in, it gets changed by its argument, and then when it gets passed back, I think we're going to see foo be foo of I squared. Let's see what happens. Serial monitor. Yeah, 3 squared is 9, 25, and then we go off the end of the array. So you can in fact change your arguments, but they have to be done as part of the array. This is being passed in by address. Prior to this, when we passed I in, we were passing in by value. So, having said that, it is possible to do the similar computations, but not as returns. And the mallocs, that is the allocation for memory, is done. That's all done in advance. So the translation from the Java to the C is not exactly straightforward. It's not one-to-one. And I think that is in general true. It's been a while since I did any C programming. How you doing over there, Kevin? So now let's have a looky-loo over here. I got my real data and my imaginary data set. It seems like there are some double precision numbers which are needed, which are set as, I'll call them auxiliary variables. N is already set. These double precision numbers I can paste in directly into my Arduino program. You know, this kind of translation is fairly ad hoc, but I'm not going to discourage you from doing it. So here's 2 pi k on n. Oh, I forgot to plug in my laptop, and now he's giving me a little trouble. Let's take a short break while I get my power cord. Sorry about that. Okay, hopefully we didn't lose everything. Let's go back in here and hit stop.